Ryan.
Hi Ryan, I'm Todd.
Do they have water bottles?
I don't really. You met Tim, he came to the house.
Okay, gang. Ready to launch the boat? Okay, first of all, if you didn't sign in before you leave, please do. That's a formality for the club's insurance. If you're signed in and you break your leg on the way out, then the club's insurance will cover you. If you're not signed in, you're not part of the crew, and they'll thumb their nose at you. So it's just a formality. Anyway, I'm Bob. I think you probably know that already. Also known as AU and a couple of things we don't talk about. Anyway, glad to see all of you here this morning. Hope we'll get some good things going. Hope to get the word out from this one. This obviously is like the intro class, if you please. We do the AC circuits. We have about twice as much stuff to lay out and to work with, and bring a couple of otoscopes and do some AC stuff and look at waveforms and all kinds of gee whiz stuff. And we always do things hands-on. We build up what we're going to talk about and actually demonstrate it in real time. So get the word out there that we'll do that one too. You should have several things on your desk there, and we'll talk about what they are as we go along the way. So, all right, with that, let's just jump in with both feet. What are we going to do today? Well, first, let's talk about what we're not going to do. For 3 hours of DC circuits, you're not going to go out here as an electrical engineer. And I think you probably know that. Basically what we're going to do is just a little bit of DC circuitry, kind of get your toe wet, see where we are with that. And it gives you a good starting point. Cindy and I were talking there about her test, getting ready to take the test. Just getting Ohm's law under your belt is a good thing for that. And you know how to manipulate that, you will when we leave here with that. We'll play with some of these different things. Hopefully when we get out of here, DC will be very obvious to you and something you can do. And you also have some practical things that you'll learn along the way. If you didn't know already, like using the multimeter, rotor multimeter. If you don't have one of those, you probably want to get one after the class. And they're just very, very handy to have around your shack, around your home, your shop, vehicle, whatever you've got. They're good for us. So what are we going to do on this? Well, you have a couple of things laying on your table already. You have a breadboard. Looks something like this. Maybe not exactly. We'll talk about that little guy. You have a little battery box. That's a little black thing with a couple of wires sticking out. Have some batteries to go in it. Have a bulb and a little switch, and there'll be a couple other things that we'll do along the way. And if you didn't bring your own multimeter, we've got a selection of meters up here. We'll talk about the different kinds of meters. You can get one of these and use one of these if you want to. And you can choose whether you want to use an analog with a swinging needle on it, or if you want to use the digital. It's just whatever you like. Those are the things that we use. And you have several handouts. There's one handout there that pretty much outlines everything we're going to talk about. And if you want to follow along with that, you can. I apologize that some of those got a little bit cruddy looking on the left side. My printers started to act up a little bit with one of the ones that didn't want to do well. Okay, guys. So anyway, but they're there. So we talk about the breadboard, photon multimeter. As I said, there are two kinds. There's analog and there's digital. The digital will have a little digital display, as you would expect. The analogs have a swinging needle that goes back and forth. The analogs are a little bit more difficult to use, a little more touchy. The digitals are much more forgiving. They've just got to work with whatever you do with them. But an analog meter you can blow up, by the way. We have, by the way, I'll go ahead and tell you this up front. We have a saying in amateur radio that whatever makes everything work in electronics is the smoke. If you let the smoke out, it'll no longer work, whatever it is. And that applies to meters as well. Somewhere along the way in these classes, we might want to consider doing a project. We've done several things in times past. We've done soldering projects, where just by a little kit thing, you learn how to solder things. The most ambitious one we ever did was we built an AM radio just on a piece of wood stock. I mean, totally built from scratch. We used brass nails in the board as the contact points and soldered everything, by hand to that. It had a little transistor-like gadget that did the AM radio part, and a little coil for that. And then we used a Darwin transistor and a tiny little speaker to give it audio. And it actually worked. And it took the full 3 hours to put that together, to lay all the stuff out and solder everything together. It actually worked. So that was probably the most ambitious thing we've done. Okay, that's the breadboard. If you look at the breadboard, The key thing with the breadboard is those two little rails, as they're called, that go down the sides. And I've got to remember, where do I go? There we go. These two go down the side. And that one that's on the screen has two rails on either side for battery power. Now, you can do it any way you want. The red normally means positive. The blue or black normally means negative. So if you wanted to, you could put a wire right in there with the red lead or the hot lead for your battery box, and you put the negative lead in there. Then that power is distributed throughout that whole line of pins or sockets that are there. Or you could put the positive in here and the negative on the other side, which is what I like to do. I like to separate them just a little bit. You can do it any way you want to. Some of these, this one I have in my hand only has a single rail on either side. That one on the picture has two rails, one on either side. Then the things in the middle are a little bit more tedious, if you please. You have 5 little holes there. Those 5 holes are connected together, but they're not connected to the 5 above or below it, so they're isolated or insulated from that. The point being then, whoops, try that again. The point being then, if I wanted to connect something together, I have 2 or 3 things connected together, I put 3 wires in one of those 5 pins. If I needed more than 5 wires, then I just jump her to the next one up, and to the next one up, and get however many we needed for that. We're going to do things pretty much manual. I have some of the prefabricated leads that you can get for these, but we're going to use some plain old wire. And if we need to strip some wire and do some things, if we have to solder something, I brought a soldering iron. We'll do whatever we need to do to make it work. Any questions on using the little breadboard? We'll do it in a minute. Okay, meters. That's an old analog meter. Matter of fact, that's something here you don't see anymore at all. Is this pin configuration. All the meters now have a banana jack kind of a plug-in instead of that little pin thing. Anyway, this is one of the old originals. It had a number of things that you would have to set manually with it. You set what the range was, what function you were going to do with it, and the 0, the ohms, if you're making resistance measurements. They're pretty manual, but hey, they work, you know. They did their thing. Then the digital ones pretty much do it all for you. You just pretty well select what it is you want to do. You want to do AC volts, DC volts, millivolts, ohms, or check diodes. This particular one would measure capacitance, or amperes of current, milliamperes of current, microamperes of current. Select what you want. It figures out the right range. It doesn't care about the positive, negative polarity. It just adjusts as it goes, and it makes it very simple. Like I said, the analog meters don't do that. With the analog meters, you have to be very conscious of polarity. If you pick it up backwards, you bend the needle, as we say, it'll bang the needle in the reverse direction, and it can destroy the meter if it's too bad. Also, if you have an analog meter and you have it set to measure resistance, and you measure voltage with it, almost guaranteed that it'll go up in smoke. So you have to be careful with the analog meters if you can't blow those up. Then this just another one there. This particular one is more manual. The previous one was auto ranging, meaning it automatically set the range as you change values. This one though is more manual. You have to select the range that you want. You want 200. I can't read that ohms. 200 ohms, 2,000 ohms. And I guess all up to mega. I'm kind of looking at it in the name. Anyway, that also has a transistor tester built in for whatever that's worth. But manually, you have to rotate the dial to get what you want out of it. Works the same as the others, it's just a little bit more manual. Now, I got it out of the way. What is electricity anyway? Right?
Electrons?
Electrons, yeah. Doing what? Moving through a wire, right?
Sure.
Yeah. But when I stroke the black cat and I touch the doorknob, is that electricity? Well, it is. It's static electricity, but it is electricity. Yeah. Okay. However, it's not something we can generally use. The electricity we're talking about is something that we have more control over, such as what comes from a battery, or what comes from an AC outlet here in the room, or some other similar kind of place like that. Wow, we run out of spots, Jerry. Can you believe it?
Well,
There's one left.
I'm happy, there's one here,
We're right there.
and I'm happy to give this one up for someone that needs the practice, so.
Okay. All right.
I guess we got the word out.
All right, this is good. I love it. Okay, and as I started to say, then going on, where do we get this electricity from? We use either batteries, generally, or from plugging it into the wall. Of course, AC comes from, or alternating current comes from a lot of places. We have a generator DC versus AC, what's the difference between the two? And here we're dealing strictly with DC, direct current, which means the current is going to flow through a wire. The electrons, Lewis said, the electrons are going to go down the wire in one direction constantly. They're not going to vary, it's just going to be a steady flow. It's not unlike putting water through a hose. You know, we hook a hose to a faucet, turn it on, and the water flows one way. You have direct current with a water hose, but you never have alternating current. You hope you don't have alternating current with water hose anyway. Versus AC, which is a whole different world and has a whole new set of complications with it. Alternating current, by name, means it alternates direction. It goes down the wire one way, reverses direction, and goes the other way, and it does that constantly. The current that we use out here runs at 60 hertz. Hertz is the new term for cycles. Way back when we called it cycles per second. Now we use the term hertz, which means the same thing. All that means is how many times per second is that current reversing direction. So it's 60 hertz. That means it's going back in that 60 times in 1 second. And taking that on out a long ways, we go to UHF radio with our little handheld, and we key that thing up, and we go out to one of the UHF frequencies. I'm just going to pick something, say 420. What does that mean? That means that signal coming out, an RF signal, really is an AC generated signal. And it's coming from the circuit inside the radio. It's alternating back and forth 420 million times per second. It's moving, going fast. And then when you get into the microwave world, and we're way up in the gigahertz ranges and all that sort of stuff, it really gets crazy. Dealing with microwaves is a whole other discussion. But it's still AC, still alternating current, going back and forth. By the way, if I say something that doesn't make sense, tell me. Or if you have a question, please just say, what about this? And we'll stop and talk about it. The idea is to answer questions and learn. Battery power, where do we get it? Well, dry cells, obviously you have 3 of those on your table. Difference between NiCad and nickel metal hydride. The old NiCads were the original rechargeable batteries. They had a really bad habit of memory. They would remember what kind of usage they had. If you only use it just a tiny, maybe 10%, and then charged it back up again every time, it would only deliver about 10%. It would die. They had a memory cycle. Nickel metal hydride chemistry changed it, and the memory, it still had a little bit of memory, but not nearly so much. Today, nearly everything is lithium ion or some form of lithium ion. And those batteries do not have a memory. They'll also keep delivering their power almost down to the point that there's 0 power remaining before they shut off. Lithium batteries are great in that most all of them, as far as I know, all of them actually have built-in protection right in the battery so that you can't ruin the battery. You can't overcharge it. You can't put a short across it and blow it up. You can't discharge it to the point that it destroys itself. It won't let you do that. Other big batteries, gel cells. We see a lot of those out before, especially before lithium ion became so popular. The gel cell was like a car battery, except it was a sealed battery. There was no maintenance to it. You didn't have to add water to it or watch for acid spills or any of that. It used a gel-type electrolyte inside of the battery, so it was much more easy to handle. Versus the lead-acid battery, which is what most of us have in our cars, or at least used to have, literally had liquid sulfuric acid inside the battery. And periodically, you'd have to take the little caps off the battery, put some distilled water in there to replenish the liquid so that the battery would continue to work. Lead acid, of course, is very heavy. It's very dangerous. The sulfuric acid will leak through just about anything. The gel cells are very, very heavy as well. The lithium-ion batteries are much, much lighter than either one of those. Now then, so we talk batteries. You've got a battery, and you hook it up to something, and the something doesn't work. How do you test a battery? Measure it, right? Measure. Let's do that. Okay. You should have 3 AA batteries laying on your desk. So grab your meter. Is anybody using an analog meter with a needle? Everybody got a digital meter?
I believe this is digital.
Everybody doing digital? Okay, I'm not going to talk analog. I'm going to just call digital. So you set your digital meter for DC volts. If you have one where you have to range it, come on up. Get any kind of, you have an analog or digital, whatever you want to do. If you have an auto ranging one, you just set it on DC volts. Sometimes the DC vote indicator doesn't say DC. It'll have a straight line with little dashes under it. The AC symbol is a line with a little squiggle in it for AC. Anyway, it says DC vote, and you put one probe on one end of the battery, one probe on the other end of the battery, and it should read how much for one of these batteries you're using.
1.5 volts.
1.5 is the target. It can be anywhere maybe 1.4 to 1.6, depending on how new and how fresh the battery are. Some of these batteries are fairly old, so they may not be that great. Hopefully all the batteries are good. I may have, if you have one that doesn't register at all, let me know.
Doesn't matter. It really doesn't matter.
Now, what about the polarity? Does the polarity matter?
You'll test it.
On the digital meter, the polarity doesn't matter. Analog meter, it definitely does. You have to put the positive lead from the meter to the positive terminal of the battery and negative to the meter. But on these, it doesn't matter. If you put the positive lead on the positive of the battery with the digital meter, it will just read the voltage. If you reverse the leads, and you can try this, put the negative lead on the positive, then you'll see a minus sign that pops up in the reading, and it'll say minus 1.5 or whatever it is. It lets you know that you do have the leads reversed. So it's not, you know, the good part is you're not going to hurt anything with it.
You should say, you should have a decimal point in there.
Now again, some of these batteries are getting a little age on them.
Try this one.
Anybody have a bad one?
I think she just did. No, you just had to say that. This one showed less than a volt. Might be her meter.
And that's
Now, we had one battery that was 0.3 and one that was 0.8.
No, and then when I tested them, like, you showed them much better.
Oh, much better, okay.
Yeah,
I think it's her meter.
made a difference.
Okay.
This is my, so these
You're
are.
not getting 1.5.
And some of these meters are not the newest as well, so that could easily be the case.
That's a good one.
No, I'm not there. The battery's good, the meter is.
1.58.
And I tried this. Hold that battery.
Oh, I turned it up.
That means that there's no bonus versus.
And this same battery is doesn't go on this
This
meter.
one problem is this battery's bad, and this battery side here.
We can share this meter.
Can you share that? Look, I can start to get you there.
You're looking for 1.5 volts. It can be negative or positive. So now it'll be bad, so it'll be a negative.
Exactly.
Now I switch your leads, or it was battery.
Either one, the same difference, yeah. And then you won't see the negative side. Everybody okay? Anybody have any doubt? We had one of the meters here had bad batteries in it. The batteries were down in the meters, so it wasn't working. And I got the proof one, if you need one here. I noticed that the gentleman at the end there had a fruit meter. How old is yours?
Do I?
How old is your fruit meter?
5 years?
5 years? Is that
About
all?
35.
Oh, 35, that's more better.
A vintage
I
1979.
think I bought mine in 82, I'm not sure. It was before 85 when I bought this meter.
Probably.
And I've used it all these years, I use this thing almost daily, and it just works.
Yeah.
So fluke it, you pay for it. And it is
Oh,
good
yeah,
stuff.
yeah.
It's good stuff.
Do the leads go bad?
Yes,
Okay.
they can. Not often, but, I mean, they're cheaper, they're easy to replace.
You have to send
Buy
it,
good ones.
you have to send it to P-Melt.
No? Well, actually, there used to be an email that, I don't know if it still is or not, I haven't checked that. All right, I'm now wired for sound. Okay, how we're doing on checking batteries, you all okay with that? Doesn't matter whether we're checking a 1.5 volt like this one, or if we're checking a 12 volt battery that we're hooked to our radios like Field 8, or you're checking the battery on your car, or any number of things, or the little button cells. I had a really interesting thing. My wife has a little 2017 Sonic with the remote, thing that you started with and unlock the doors and all that. And it got to the point I had to almost be right up against the car for it to work. So I said, okay, the battery's getting weak. Used the 2032 button cell. That's a 3-volt button battery. And I had a bunch, and so I changed it out, and it wouldn't work at all. And I thought, okay, maybe that battery I tested it, read 3 volts, it was good. Got another new one, put it in there, still wouldn't work. And I just wasn't really ready to give up on that, so we were at Walmart a couple nights ago, and I bought a package of 2 brand new ever-ready 2032s, put it in there, and the control works like a champ again. So what does that tell me about my measuring the battery voltage on that little coin cell battery?
You had crappy batteries?
Don't let the batteries get too old, that's one thing. No, seriously though, when we measure a battery with a meter like this, we're not putting a load on the battery. So it can read the full voltage, but when you put a load on it, then the voltage just takes a nosedive. And the little battery doesn't have enough capacity left to deliver its voltage like it's supposed to. And that's what was happening with that. Those were old coin cells. I'd had them for a while, I knew that. But they tested good, you know. So I'll always take these measurements with a grain of salt.
Kind of like you get up in the morning, it might not be any problem to pick up 150 pounds carried across the living room. Do that after you just ran a marathon. It may not be so easy.
Exactly. That is exactly correct.
Talk
Okay.
about today.
We good with that? Moving right along. Let's talk about some resistors. What is a resistor?
They resist.
They resist. What do they resist?
Low current.
Current. Okay, let's go back to the water hose analogy again. Current is much like water hose. You have a source over here, which would be like our battery that's supplying the water, which is the water through.
And the resistor is your thumb over the end of the hose.
I'm sorry?
The resistor is your thumb over the end of the hose.
And your resistor not putting your thumb over the end of the hose or putting a kink in the hose. Or Jim had an illustration, a picture that he sent to me, where they were using some sand. They put some sand in the hose. Does the same thing. Puts a restriction in the hose, so a resistor would slow down and limit the amount of current that could, or water in this case, that could flow through the hose.
Like cholesterol.
A resistor does essentially the same thing in a circuit. It reduces the amount of current that can flow through that circuit. Why would I want to do that?
Protect something?
Protect something? That could be a reason, yeah.
If you're using
control it.
something that doesn't need that much.
One of the really widely used functions of resistors is a voltage divider. I can take 2 resistors, hook them together, put a battery on either end. We have a certain amount of current flowing through there. But if I measure across just one resistor, I don't get the full voltage. If I measure across both resistors, I'm just measuring the battery. But if I measure one resistor, I'm getting another voltage. So I've got here we put 3 these batteries in one of these little cases. That'll give us 4.5 volts. But I only need 1 volt for some reason. Then I can take several resistors like that and get a voltage drop of 1 volt across one of those and use that 1 volt in whatever I'm doing. That's one use of it. Also, they can be used in conjunction with other components, capacitors in specific, to create an oscillator, which is a circuit that will generate AC and a frequency, go back and forth for us like that, just using resistor and capacitor. Because the resistor resists the flow of current and the capacitor wants to soak up the current, it will slow down how fast the capacitor can receive its charge, be fully charged. The smaller the resistor, the faster it charges. The faster the oscillator would run, if you please. And we'll talk about that when we do AC circuits. So resistors are very valuable. They're used for all kinds of things along the way. How do we measure? Well, first of all, what unit do we use to measure resistance? Ohm, OHM. That was named for a guy whose last name actually was Ohm. And basically it's just almost like an arbitrary number that we've come up with. We see values of resistance anywhere from a few tenths of an ohm up to millions of ohms, mega ohms. So you can see them all over the place. How do we measure them then? Well, there's 2 ways we can go about this. Your resistors have a color code. I think, did we put out, we put out resistors, didn't we? Okay, I'm getting a little ahead of myself. We'll talk about the color code here in just a second. But anyway, we can look at the color code and figure out what it's supposed to be. But most of those color codes have a tolerance color at the end, which says what's the tolerance of this value. So this resistor is supposed to be 100 ohms plus or minus 10% tolerance. So it could be anywhere from 90 to 110, still be a good resistor according to that. So then we would measure it with our meter to see what it really says if we needed to do that. So that's how we measure. How are they rated? They're rated in watts. That's how much power can one dissipate, how much one can a resistor handle. We see 8 watt, which are tiny little resistors, quarter watts, half watts. I think the ones that you have are half watt resistors. 1 watt, 5 watts, 10 watts. They're all kinds of large sizes depending on what you're doing and how much heat it needs to dissipate. Because when you restrict the flow of current with a resistor, the resistor gets hot. That dissipation is taken care of with heat. It's dissipated with heat. Now, what about series and parallel? We can do a lot of crazy things with, I'm trying to figure out where did I put my marker. I don't have one, I guess I didn't have one. Give me a marker. Hope it works, we'll find out. The symbol for a resistor is something like that, just a little zigzaggy line with something like that. So with that I have a single resistor, and I can hook up resistors either series or parallel, depending on what I want to do. If I wanted to put them in series, I would just take another resistor and hook them together like that. So let's just give some values here. So we have 200 ohm resistors, 100 ohm resistors in series. In series, the values will add. So if I measure from end to end of that, I'll see 200 ohms. Easy enough, right? Pretty straightforward. I must be losing. I know I had a brochure somewhere.
There was one up there.
Yeah.
It's out or something.
There's a rag at the end.
Yeah, try that.
Dirty rag always works. I had a brochure. I'm not sure where it went now. Okay, so let's just take one of these guys off. Okay, so then that was in series. If I wanted to put it in parallel, then I would connect these two together like that. So when I hook them together in parallel, then the resistance will be less than the smaller value of the two. If the two are equal value, then it will just half. So the 200 ohm resistors, if I measure end to end, if I measure from here to here, I would see 50 ohms. And there's reasons for doing series, there's reasons for doing parallel. For example, in parallel, if these were 1 watt resistor each, then when I parallel them, I would have a 50 ohm 2 watt resistor, which gives me a little bit more oomph if I needed to do that. Okay, now then, that's what we're trying to get to. Let's look at the color code. In your handouts, you have a color chart. And there's two different standards that you see there. Some resistors have 4 bands, some have 5. But they all work essentially the same way. So you have brown, black, red, so forth. So you look at the little bands on your resistor. You put the silver or gold, if it has a band like that, onto your right. You put the other colors on the left. And then you just read the color values and see what the value of the resistor is. So what is the value of the resistors that you have? Everybody figured it out?
It looks like 1, 0, and then 10 squares.
1, 0,
And then
and 2 more zeros.
10 squared.
So 2 zeros.
Okay.
1,000 ohm. What's the tolerance? They're
Plus or minus 2%. Well,
gold or silver or some color band at the end after that.
Gold.
Then multiply by 100.
Use gold, which is 5%.
Oh, I see. Well, it definitely can't be colorblind, so it looks like brown.
Yeah, you can't be colorblind. How about that?
It looks like brown, black, red, gold.
Okay, so we got brown,
Am I right?
and then red,
Brown.
and then gold. Okay, that's what it, I think all these will be the same, unless we got one mixed in somewhere, they should always be the same. So if this is true, what is the value for brown? One. What is the value for black?
0.
What's the value for red?
2.
2, that's how many zeros we're gonna put on it. So it's gonna be 1, 0, 0, 0, 1,000 ohms. Then what is the next band? He had, and this one's gold. Gold is 5%. You can look on your chart, you see gold, there's 5%. So this is 1,000 ohms plus or minus 5%. What's 5% of 1,000? 50. Which means it can run from 2.
90, 50. Or no, yeah, 90.
I got it backwards. Between 950 and 1050 would be good. That's all there is to it. It's really all there is to it.
I haven't got that.
Now, I'm going to go ahead and do this even if I get in trouble. In the old days, we had an acrostic to remember those colors. There have been some others that have come out that are probably less offensive than the ones I learned.
Mm-hmm.
I can't even tell you the one I learned. If I get in big trouble.
Yes.
Yep. So anyway, you can find one of those. There's all kinds of little acronyms that you can use out there for that if you look it up. Let's look up color code. You'll find one that you like. It's not offensive to you.
I thought you were going there, I wanted to hear it.
No, I'll tell you offline something. Okay.
Should I have ever heard it?
We make extensive use of the metric system, as you can already see. So instead of saying this is a 1,000 ohm resistor, what I would normally say is that this is a 1K ohm resistor.
That makes more sense.
K meaning 1,000. Okay? Now, what's the difference between 1K like that and 1K like that? Small K.
1024 versus 1,000.
Okay. Well, actually, I should have used the deal. I'm sorry. I'm getting myself mixed up. 1 M.
Hey,
This
Bob,
means million or 1,000.
here's one that everybody can learn. Bad beer rots our young guts, but vodka goes well.
There you go. There you go. Yeah, that'll work. Get some now. Gold, silver, and none with color bands. Add that to it. Okay. Anyway, so we multiply. We use 1,000. 1,000 is very common. Kilo, K, mega or mega ohm, millions of ohms, millions of. Hope you don't get into megavolts. That's bad. That's lightning territory. And then we'll go the other way. We use lowercase, milli, 1,000 micro. Now we do see lots of micro, especially in capacitors and inductors. We'll see microfarads and microfarads or picofarads and various other things that we use for those things. Micro is the most common, however. Questions on that? We're okay with that?
So does the flex capacitor work at the mega ohms?
Flux capacitor usually works in kilofarads. A farad is a measure of capacitance. 1 farad is bigger than anything you can imagine. These flux capacitors, special amplified type capacitors, basically have humongous value.
You're staying in the present.
So how did you get the 8 for the red?
Pardon, please?
How did you come up with the 8?
It's actually not an 8, that's 2 zeros together. He was
Oh,
right.
it's 2 zeros.
Oh, it's 2 zeros together.
0, 0, 1,
Red is
1.
10 squared before 100. So you're literally taking the first 10, multiplying by 100, so you have 2 more zeros.
Okay. Are we okay on that? Kind of buzzing right over. Hey, guys. Okay, now let's see if it really is. So how are we going to use a crazy multimeter and measure this resistance? Well, you set it to the ohm scale, and this is a 1K ohm resistor, so that's a fairly low resistance. So that means you can use your hands and hold the probes on each end of the resistor, and it's okay. Now, if you had a 10 mega ohm resistor, you couldn't do that because your body has a certain amount of resistance in it. If you get into really high resistances, then it will throw it on. But for this, it won't matter. So you basically just attach a probe to either end of the resistor. Your meter set to ohms, and it should read out some ohm value. Now, if you have to set the range on your meter, then you set your range to either K ohms or mega ohms, so it has enough range to pick it up. And if you play with the ranges, you set it on the mega ohm range, then you may get a fractional value of a fraction of a million, tenth of a mega ohm. Are we okay?
Yeah, actually it does. She had a good question.
Yes.
Does her body affect the resistance?
If I'm holding it.
Not on this value, no. Now, if, as I said, if that were a 10 mega ohm resistor, then your body resistance would come into play. Oh, you wouldn't feel it.
So to measure 1,000 ohms, our range should be set at 2,000.
Okay. Now, by the way, there's several people here who've done all this and are experts at it. If you need a hand with it, grab one of them and we'll, Tim's one of those, probably several others here as well. If you need a hand, we'll certainly give it to you.
I think so.
Are we okay? Anybody having a problem?
Looking for 1,000 ohms.
That means you're either the resistor.
Also,
Okay. That value wasn't that.
We got, probably put 950, or no, we get 999.
About 990.
Right.
Okay, that's good. And two, these meters are not so stacked.
This thing doesn't click between increments right now. It just slides.
Maybe I'm just.
So is this ceramic? This was some ceramic?
No, it's not ceramic, it's just ceramic. You can get a ceramic resistor. By the way, she did something that you can also do if you want to do this. Plug your resistor into the little breadboard, so it holds it, and then just stick your probe into either end of it. And you don't have to touch it with your fingers.
It isolates it, yeah.
It works. And if you're doing a large value resistor, that would be the way to do it. If you're doing a 10 mega ohm resistor, yes, plug in the board and measure it. Everybody okay?
No.
No, okay. Anybody get any resistance values that are way out of left field? Like instead of being between those two values of 950 and 1050, you got 700.
I hit the mode button.
Way out.
Or not continuity.
I don't know which one was number.
Five isolated on this side, and then all of these are also virtually connected. Then the power inputs, this is like
Good. Anybody got a hiccup that we can help you with? The one leak you hanging. It's just important. Okay, ready to move on? Okay, just a real quick little thing here. Let me back up, way back up. Just a second to that. Okay. When using this thing, this line of pins all the way to the top is all connected together. The second row of pins here is all connected together. They're not connected crossways like this though. And the same thing over here. This line is all connected together, that line is all connected together, but they're not connected to each other. These 5 holes are all connected together. They're not connected to this or anything over there. These 5 are totally independent. So if you plug your resistor one end in here and one end in there and measured it, you can get zero basically.
Shorted it up.
Because it's shorted out, it's essentially shorted, that's the definition of a short. You shorted it out, because you're measuring the resistance of the actual pins inside that board. So what you want to do then is put one end of the resistor somewhere over here, one end someplace over there, and then just put your probe against the unit inside of the resistor. So, well, those FYI. We'll talk about shorts and openings a little bit later. Lamps. Well, we're a little bit in the antique world right now. We're using filament type lamps today. We're not using LEDs. We'll do LEDs when we do solid state. But for right now, we're going to do it the old way with the old filament type. What is a filament type lamp? It basically just has a little element in it. It gets really hot and it glows.
It's a resistor.
Thomas Edison's been years developing that technique. Finally got it to work. Now, filament type bulb. How would we measure the resistance of a bulb? If current's going to flow through this filament and make it hot, make it light up. So how do we measure a bulb resistance-wise? Same way as a resistor. Just take your meter, put it on one side of the lamp, put the bottom side of the lamp with the other lead, measure the resistance. You get some value, whatever that value happens to be. I don't know. So I take my trusty little old lamp, and I take one lead of the meter, put it against the case, something like that. Take the other lead and touch it to the bottom end of the lamp, and I should get some kind of a resistance reading. Let's see what I get just for a minute. I'm showing 1 ohm on mine. What do you guys show? About the same?
5.
5 ohms? Okay. Somewhere between, a fraction of an ohm all the way up to maybe 5 to 10. Now, that's with nothing going on. What happens to a resistive element though when you heat it? What?
The resistance goes up.
The resistance goes up. So how am I going to measure the working resistance of a lamp? Can I do that? Yes, we can do that. We'll show you how here in just a little bit. The point though being to remember that statically with nothing on it, you're going to get a basic value, a very low value. But when it's under power and being lighted up, you get a different resistance reading for it. If you can read the resistance per se, we'll have to calculate it because we can't really read the resistance when it has power applied. But we'll do that when we get to it. So we got a little dinky light bulb there. How are they measured? How do we rate these things? Well, normally they're rated by the voltage that's required to make them light up. I think most of these that we have are either 6 volt or 3 volt. I'm not even sure what they are, quite frankly. Usually have some kind of part. Remember, this is the Chinese knockoff. It doesn't have a number. Yes, it does. Number 14 stamped on. I have no clue what 14 is. But anyway, now you also have a lamp holder there that you can screw that into. So if you want it, you can also screw it in the holder, measure the 2 terminals on the holder. It works the same way. Now, so you measure it, and instead of getting 1 or 2 ohms, you get nothing. What does that tell you?
Open.
It's open, the light's burned out, the bulb's burned out. So when you have a light bulb at home, and maybe you still have some old style light bulbs at home. I know I still have some. Some of them are frosted, you can't see the filament inside the bulb. If the bulb doesn't light up, and you turn the switch on, take it out, and measure it with your meter. If the meter says it's got resistance, then the bulb's good. If it reads open, that is infinite resistance, then the bulb is bad. It's a quick and dirty thing. You can do this with automotive bulbs. You have a little tail light and turn signal lights and all those. A lot of vehicles still have filament type bulbs instead of LEDs in there. Do the same thing with those. Sometimes bulbs can be deceptive. The filament can look like it's intact, it can look like it's good, but it has a physical small break in it that you can't see with the naked eye. And it doesn't work, obviously. So that's just something to watch out for. Then like bulbs are also rated by the amount of light or lumens that they put out when they're fully lighted. We see the lumen rating become more important with the LED lights than we do with these. These basically just, they work with them. Okay, so we measured with a VOM. So how are we gonna make this thing light up? Well, that's the next project. Okay, before we do that, we need to power up our little battery box. You have a little black battery box. Slide the back cover off with your thumb. And then you put those 3 batteries that you have in that little box. Now, you have to watch the polarity. You have to put the plus to plus and the minus to minus in the box like it shows. Otherwise, it won't work. So put the 3 batteries in, arrange them the correct polarity, slide the cover back on there, then measure with your meter, measure the voltage out of that. See what kind of voltage you get. You should get somewhere around 4.5 volts.
There may be a power switch on the back of your box.
And there's a power switch on the back.
Oh, good call, KC5
The power switch has to be on the ON position. Yes, glad you reminded me of that. And you should get about, like I said, about 4.5 volts.
That's gonna be the, yeah, turn all the way off, right?
And Bob, the meter should be on the one with the line.
If you're using a digital meter, it's got a little straight line with a little dash, not the one with the weightage for AC.
They are working in series, so the voltage is
Doing okay?
These are in series, so they add together. So what's 1.5?
Okay. Everybody getting about 4.5 volts, give or take a little. Everybody okay? Still a couple people still working on this. You guys are okay? You guys okay? You guys are all okay? Are you okay? Okay. Now the next thing is hook it up to the lamp. The problem we've got right now is that some of you have a lamp holder with no wires, correct?
Correct.
Just have a naked lamp holder, looks like that. Woo! Okay, you should also find some twisted wires, looks like that, laying on your table. Where this is manual, okay? So you're gonna have to take those wires, untwist them. And then you're gonna have a pocket knife or something to strip about 1/4 inch of the insulation off of each end. And then we're gonna loosen the screw, put the little wire around the screw and tighten the screw back down. You gotta do that twice. And I have a couple of screwdrivers up here.
You made her whip out her knife. But you don't want to use that to screw.
No, I don't go my way.
You're good. I mean, I think if you would just understand that, that's what he's
So
talking about.
basically, you use your wire.
There's a couple of screwdrivers, you can use the screwdrivers. If you don't have a pocket knife or you don't feel comfortable doing that, cut your thumb or something, I'll be more than happy to do it for you if you do this.
One wire to go to the base and one wire to go to the port.
There, happy.
Lance is like, ooh.
No, and you know which wire goes to the wall.
Actually, they don't know for it.
It would be easier.
That bolt should light up either way.
Did you eat harder? Fine,
So-
here you go.
One of those connections to the.
Because they need to stay there.
Sometimes this kind of stuff is your dexterity.
Really, you're making a connection between these two roads. You'll see the door.
No, they're not.
And use that switch.
Everybody doing okay? Anybody need any help stripping the wire or pretty handy with the pocket knife? Sometimes I cut gashes in my thumb with the blood, makes it easier to see the wires. Jerry uses your teeth. Okay.
You can go all the way up to at least
All right,
9
now
volts.
then, once you get the bulb set up, or if your bulb's already set up, you're fine. We want to hook it up with the breadboard. Hook up the lamp with the breadboard. Hook the battery, one side of the battery to one side of the rail of the little breadboard. The other side of the battery to the other side, and then hook your light bulb across those two same things and see if it lights up. Use the breadboard.
This one is surgery.
It's redundant, because you have a switch right here. And I think we just take this.
Oh,
The light bulb is not polarity sensitive, so it doesn't make a difference between your. And then the hook will go in the way where the screws tighten this way. We're going to wrap that right around the screw.
oh, turn the battery on.
Everybody okay, getting everything hooked up?
Ever make sure you got her back on.
Yeah, you can turn it on and off with the switch on the battery. Larry Howard. Ask Jerry.
There's another set right here. So I could either do that, or I could see what
Oh, yeah.
That one. So this
Like I said, everything is sprayed across, it's the same.
is not connected to the outer rail.
So,
But I guess this applies equally to every service power line.
Anybody need a hand?
no,
Just
just
help.
brain.
Robert circle lift around, he'll help.
This is the same.
Oh, I see.
And these have to be on the same level.
Everybody okay?
Series, right?
Yes, everything is in series.
But it doesn't matter as long as we're in the same road. Okay, yeah. Those are all the same. So this
listen to. So, I was in water, so you use that level, measure there, you go, make sure when you remove the load, it's called the level.
Yeah.
It's gonna say measure the resistance in ball flow.
I'm gonna get a bad reputation. This is hard.
I'm so glad I bought this. It's not
Yeah, 4.6, you're good there.
Batteries.
Yes,
Alright.
it's 10 o'clock, it's maybe here.
It's popular.
Yeah, it's going from here to here, and then it's gonna go to here, but it's gonna have to go through there.
So there's not a connection.
So that it doesn't matter where on the road, you know.
Thanks for your people.
So what did you say? How should you feel the
We should be shining.
Either that, or there's an
This
issue
side,
with how the wires, go back far enough, you mean,
He
you
researched
turn
them.
out last, oh, okay.
Research them further. Still not.
When you say strip it,
I don't know, you bring a
is that over
screwdriver
time,
too?
you know, it's just.
Jose, you made it.
I made it. How are you doing, sir?
Is it-
This is my son again.
Oh, yeah, I've talked to you on the radio. I'm Todd. Good to meet you. Ian. You learn a lot?
He's sleeping. I'm walking toward it. Went to the breakfast. Hoping he can pick up at least a few details.
Soak it all in.
Yeah.
It all makes sense eventually.
Exactly.
Sometimes not right away, but
Oh yeah.
eventually.
It took a while for me to pick all this stuff, so it's not. Today's just planting a seed.
I had this training in the Air Force.
Yeah.
I mean, it's for 30 years, but I never really used it.
Really?
So it makes sense, but there's always something like.
If you don't use it, just fades away. You can pick it up later, but yeah. I use it every day, so to me it's second nature.
Yeah, that's a big difference.
So
Well,
what were you doing in the Air Force? Was it more mechanic stuff?
My first job was in avionics, so airborne computer systems and electronics. And that job has two parts to it. One of them's on the flight line troubleshooting the aircraft, but a lot of times you troubleshoot it down to just a black box. And then you take that to the in-shop guys that really learn this. They get out and use an O-stroke and a multimeter. We use a breakout box, simpler than these. And you can put it in line with the system on the airplane, and it has all these test points. So we used a breakout box to find
Yeah.
which box was bad.
And then replace it.
Yeah, just swapping boxes. That's the extent of how much I use the knowledge.
Okay, I see. Yeah.
If I would have been one of the in-shop guys,
You would have to make the bulb. Yeah, I can see.
you'd have to fix the box
Ah,
and then turn it around so it's a part that they can swap on the airplane.
oh, so you will fix the box. So this will be recyclable.
Yeah. I mean, they have their own part depot on base. So when you pull a bad part off an airplane, they take it to the shop and fix it, and then put it back into the supply chain. So when that aircraft fails again, you can.
Yeah, yes.
Sometimes you troubleshoot by just swapping the box. So you don't really use your skills. But I only did that for 3-4 years.
Okay.
And then I became a medic.
You became a medic or a manager?
I was a medical technician.
Oh, medic. Okay. Yeah. Yeah, no voltages there.
No. Well, your heart.
Ah, that's the one.
Yeah.
You may need to jump it up.
Your 12 lead EKG was measuring voltages across the heart. But then I was a recruiter for 10 years, so that was really the most of the time. But
I see.
yes, you can cross training. It just depends on the needs of the Air Force.
How long were you there?
21 years. But this was the most interesting, the electronics. You know, get into ham radio, you can lean on it. I'll never build a radio, or I'll probably never make an antenna.
Me neither.
Off the shelf for me.
Yeah, see, I'd love to do that. I did that part when they did the AM radio. I'd love to do that.
It's fascinating. It is.
That one is simple enough. That would be fun. But once you start getting into, you know, like the whole thing with VHF, UHF, and modulators,
Right. You
that
got to know where it's safe to play. You have to know what kind of power supply to use for each radio. So that's kind of important. I mean, I've got I think it's a 50-watt power supply.
50 watts?
50, I think so. To power my portable radios. So in the house, using it as a base. So I got to know, you know, what kind of power supply I'm going to need if I'm going to add another radio. So there's definitely practical uses for this.
Oh, yeah. Well, and this stuff is, again, I use it all the time, so to me it's essential. But I am certain you'll come across other things where you can use it.
At least to understand it
Yeah.
and not blow anything up. Melting.
Is Jerry having light issues?
I'd take them back there, but they do.
A lot of these people you'll recognize by their voice, like Larry. If you listen to the net.
Yeah, that's what I was asking you to do.
If Larry started talking, you'd really recognize his voice.
A short switch that can,
You don't work together on that.
Yeah,
it's
yeah.
a powerful.
Okay, gang, I'm sorry, we're gonna have to talk about we're on. Some of you have already done this, and if you have, that's fine. We want to add a switch to it. We're talking about switches just a little bit. We have 2 different kinds of switches out there. There's a push button switch and a flip switch, a toggle switch. They do the same thing. We want to add a switch to this thing. Notice the little thing up there that says SPST. It's one of those infamous acronyms or abbreviations we use, which means single pole, single probe. That means that there is only 2 contacts on the switch we're going to use, and they're normally open. NO means they're normally open. We want to activate the switch, we close it, then it becomes floated. If it was always closed, it would be an SP NC, normally closed. Anyway, we have an normally open switch, and you push the button on the switch, the light should come on. That's it in a nutshell. Except for Jerry, we got a problem with her battery box out, and I don't have any good batteries for me. I think she's
Oh, there's extra here.
It could just be the wires on the battery box. There might be a break in the wires, huh?
Okay. Don't want to get too far. Everybody get something at least semi-working? You do something here real quick, please.
The switch goes to the next one. First of all, what happens if you put it? They're both going together, so it's not gonna be the same. What's going on? Why you don't work?
If anybody wants a water, there's some back here in this phone line, just help yourselves.
Both leads are connected.
I would have brought cookies, but I figured it was
We can do it back where this was supposed to be.
Just spray it for breakfast.
Well, this is the sample thing that goes through this, this only.
So simple.
You know, we're on dirt battery
Push it down,
box.
obviously, it's gonna pull
Try
that,
to be
pull
one,
that,
so I know.
which will make the power, the battery,
Oh, well, hang on. You had both battery terminals on the same. No.
So the.
In fact, that's the battery.
Is that referring to?
Just an odd circle.
This is part of the problem.
Once it goes
Did you? I took a digital electronics so far. I took a digital electronics. So what is this?
Okay.
What happens if I take
And
this
Not that fast.
No, you're not doing it because that's actually a separate throw.
Now, the switch should away. So current.
But each one of these short. So the power would be right here.
Well, you can tell me what I'm
So that's what we want.
Hey. We have a combo.
You might be short.
So we barely did.
No batteries.
Because they were plugged in the row.
That's probably not what it's-
Why? Yeah, I know I was in the bathroom.
It's not the.
Oh, no, you didn't kill the batteries. This one was in backwards.
I was gonna run it last time. So let's see if that works now.
Forget when you don't kill the batteries. They work that internal. So maybe it is.
Now they're all connected in.
Yeah.
Oh, this is 5 because it's thinner than 2.
And they have those jumpers, things too. Yes.
On the outside, this whole row is connected. This whole row is connected.
Thank you, Bob.
All right, success, we did it.
Thank you.
We had the rest of it reserved, so we got it.
I got it working.
And one's for 6 months and one's for 9. These have letters.
Pretty good with it.
So I just said 6. That's 6. This is 6 put together.
We found the problem.
The reason that there's a gap.
From that happened.
Oh, yeah, so this way is using.
To do it all the time. And if you.
Normally, my billboards are made of this sort of pattern. And you'll see.
You know, if I was just saying, it's up here, that's what I'm going to.
How does this isolate?
And there's a set of cowbells as well as you're gonna have all the other things like this. So often if you were doing something like this, you go, hey, I'm gonna go to the store some, but I don't here, needs, you'll often have these things. Sometimes you might go, set up your picture of these keep connected to your battery, connect to the outside bottom here, and this is, you know, it is also switch.
You don't want it to process
We do that too.
Okay, gang, we're doing okay? We're all right. Let's go ahead and do something else. By the way, quick show of hands, just because I'd like to know, how many of you have never hooked up a battery and a bulb before, but you the light come on? How many have never done that before? Okay, that's fine. I'm just curious that I find that there are people that never did that. That's okay. Okay, we do the AC class, which is on down the ways. When we get to that one, we'll talk about inductors, which are coils of wire, have a special capacitors, which are basically two little metal plates close together with an insulator in between. It can hold a charge of electricity for a short period of time. A diode is what we'll get to. We do the solid state class. The diode is like a one-way switch. It allows current to flow only one way through it. And then transistors are used for all kinds of things. They can act as a switch. They can act as an amplifier, act as a buffer, a lot of different things they can do. We also have a vacuum tube class if we're going to do that one. Now, it's not possible, let me rephrase that. It's not practical to hook up vacuum tube circuits in a class like this. First of all, you're dealing with high voltages when you do that. Normally, the voltage is running the vacuum tube will run 90 volts and more. So you can get a pretty nasty shock if you're not careful. So we don't show you. But we talk through the tubes, the kind of tubes, and go through the flow of signal through a radio, and you kind of get the whole feel of it. And if we do integrated circuits, we'll hook up some ICs, play with those things, and see integrated circuits, how they work. We have a 555 timer class, and 555 is a tiny little integrated circuit. Then as an oscillator built in, you can do all kinds of crazy stuff with triple different circuit. I've got a bunch of those. That's something we can do. You also can do a digital class if you want to. We talk about AND gates and OR gates and NOT gates and flip-flops and all the stuff that goes on in the digital world. And we'll go through all that. And we actually demonstrate that. We'll actually breadboard up a little circuit to show what an OR gate is. An OR gate means if this happens or this happens, turn the light on. Either one. An AND gate says if this happens and this happens, then turn the light on.
This is an answer.
And there are all kinds of combinations of that. And we do that with ICs and actually read up more of those things that we do the digital class. So there's lots of stuff out there we can do. Now, we're not through here yet this morning. We got a few more things to do. Ohm's law. Here we go. That's it serious. The three terms we're dealing with here is the voltage represented by the letter E, which comes from electromotive force. How's that for a mouthful? I'd much rather just say voltage. It's easier to say it electromotive force. But we use the letter E to represent this. Current is represented by the letter I for intensity. Current is the amount of water flowing through the hose. Current is the amount of electricity flowing through the wire. And then resistance measured in ohms is that which resists the flow of current through a particular circuit. Okay? Now, so E is equal to I times R. We call that the EAR formula, just to make it easy to remember. EIR, I times R. Little quick algebra. Then current is equal to voltage divided by resistance. So if we know any two of those, we can figure out what the other one is mathematically. Or R is equal to voltage divided by current. So how do we do that? Well, let's take a look. Couple of tidbits first. If resistors in series add in value, we talked about that before. If we put 200 ohm resistors, one hooked to the other in series, they just add up. 200 ohms to 100 ohm resistors give you a total of 200 ohms. But when we put them in parallel, then it comes a little different. In parallel, the effective value of resistance will always be less than the smallest resistor in the parallel circuit, whatever that turns out to be. If the two resistors are equal, 200 ohm resistors in parallel, then it makes it simple and just divide it in half. So 200 ohm resistors in parallel would be equivalent to 50 ohms. But that's not always the case. Sometimes you got 50 and 100 and 1,000 all in parallel. Well, first of all, you know the total effective resistance will be less than 50 ohms, and it's always less than the smallest resistor. But to figure it out, it's a little more complicated. Use that crazy formula. 1 over the first resistor plus 1 over the second resistor plus however many resistors that you have. And then you get the actual resistance. Now we'll play with this a little bit more. You have a little color code wheel there. This actually includes power, heat. We measure the effective use of the current flowing through the given voltage. That's power in watts. So that's also part of Ohm's law. We don't talk about that specifically here. Anyway, it shows you the different things that you can do with it. If you know that in the top right quadrant of that circle, if you're looking for amps, and you know if you have the voltage and the resistance, voltage by resistance, that'll give you the amount of current flowing. And you just go around with the wheel there. That's what that's for. To figure out which one you want. Okay, so we put together a little circuit like this. Think you can do that? Your breadboard, put the power to it. Okay. 1K, you have 3 1K ohm resistors already, or you're close to 1K ohm anyway. You have 1K by itself, and then 2 1Ks in parallel across the battery. And the interesting thing about these things, of course, you can always rearrange them and make them look different. I can't keep up where I put them.
Question is, what's the resistance? Figure out the resistance. We have voltage, you don't know the total resistance now.
Are we doing
So the first one's asking you for the resistance. So you need to figure out what the resistance is.
If it makes it easier to see, we can rearrange it a little bit like that. Does the same thing.
Parallel, so it's.
By the way, anybody in here Navy, ex-Navy? Nobody Navy?
They might be, but they just don't want to admit it.
Navy? Well, those usually tidbits. The Navy teaches, at least they used to teach in their schools, I'm not sure if this is correct now or not. The Navy used to teach current flow that flows from positive to negative. Everybody else in the world says it flows from negative to positive.
Well, that's electron flow.
Pardon?
That's, electron flow is negative to positive.
Negative.
Current flow is positive to negative.
Right. So, always just do negative to positive to keep it simple. So in this dynamic circuit, wherever from downward flow battery through all the resistors back to positive. Now, what is the, first of all, what is the actual value? If I didn't have the battery hooked up, I'm free the circuit, and I hook my meter here, like that, to measure the value, what value would I measure? How do we find out? Well, we know that two resistors of the same value in parallel in hand. So the effective value of this is $500.
And then.
Okay? And 500 ohms in series with 1,000 ohms would be $1,500, right?
I just don't, when you say half, you have to only take half of one resistance.
Half of one of the resistors, basically.
That's the, it helps to clarify
Okay,
that.
so that's what we're looking at, $1,500.
So now we
No,
know.
but don't this look like?
Now, if this voltage we're using 4.5 volts, that being the case now, we know the voltage across it. We know the total resistance that it has across it. In fact, what we don't know is the current. What was the formula for current? I equals,
Correct, so you, it's going to be parallel.
somebody look it up. What's the
Voltage divided by resistance.
voltage over resistance? Is that correct? Okay. So the voltage is 4.5 divided by 1,500.
Voltage,
And then I want to have,
it's not 6 volts.
and then they say.
Somebody got a calculator?
One and one, one and
You're using 4.5 volts?
That's what we have here.
Yeah, that's what we have.
Or what we have?
Yeah.
I'm using,
Yeah, well, originally I was using a four volt, a 4 battery voltage, and I didn't have enough 4 battery voltage. Okay, so 4.5 divided by 1,500 is how much?
3 milliamps.
0.03. 0.003.
All we have is we don't have,
So 0.003 amperes.
all I've got is this.
Now, we don't normally like to deal with numbers like that. So instead of calling it 0.003 or 3,000ths of an amp, we'll say that it's 3 milliamps. Is that correct? Use your own interest.
So you can't,
Okay?
you gotta get, make sure you don't.
Now, if you go ahead and breadboard that thing up, leave the battery off to begin with, or leave it disconnected. Go ahead and breadboard it up and then measure, see if it really works out that way. See if you really read 1,500 ohms all the way across the circuit, and then see if you really read 500 ohms just across these two resistors by themselves. Go ahead and give that a shot.
This side is parallel. This side, those two resistors keep showing us.
we want us to have 2 resistors in series and 1 in parallel.
Okay, about 2 in parallel, and in series with those two.
I'm just trying to visualize that.
Here,
So you have-
Plus, 2 ways.
That's short.
First resistor. Plus, minus.
resistor. Now we're gonna take the two resistors, plug them in, and plug the other same row somewhere.
With this one, put it on there.
These five are independent of each other. They're not connected. Put it in the same hole.
That's what we didn't have a wire hanging out of this.
Alright, so now you got the single, parallel. So we measure the single, we should do something else, if we measure across here.
I just had it.
I got all the way to the whole other side.
It's really, really important that we don't have power.
That's what it is.
Exactly.
Correct. So if you did this like from here,
It should be 1K. If I'm here,
they think sometimes
out of a 20K range, it's like 1.
I've got a box.
It's usually probably they're gonna hold. These things here, they can probably just measure. With this one is already the number that I'm saying, you take the road and put it actually on the red board next to it. And say you're there, you can say the top, right? Because the problem is what this one's doing is it's reading the range one, and as it's changing, it doesn't know what value.
Not only will we never, probably never use it, but it's
So basically, until you have, that's not the
Okay, so good point here. Why do we do this? Why are we doing it? Help us remember how it works, really. And especially if you're taking taking one of the tests, and you get into onslaught, you don't feel intimidated by it. It's like, I know what a series circuit is. I know what a parallel circuit is. I know how good it is. What everybody
will you ever have 3 resistors in parallel?
Sure.
Yeah, that just goes at
I just
1/3
was
of
thinking we did it.
the lowest value.
If they're all the same thing.
Because it's in parallel, it's not safe.
Of the lowest.
Well, now if it goes 3 1K in series, I mean in parallel,
One
it'd
of
be
these,
325.
in the same row.
Put 100 on and 1,000 on, and it'd be less than 100. It would always be less than the smallest resistor here.
But can you actually assign a value to it, or do you just know it's gonna be less? That makes it-
Well, you have to use that fuzzy formula.
Oh, okay, never mind.
Use that formula.
I took a picture of that, she was trying to find I could never.
you got 10 and 10 comes down here, 10 and 10 comes to a third. So the more you have, the more it's
Question was, in 100 and 10.
Anybody got a question or anything, or anything I can help you with?
I ended up.
No.
You okay?
I get 1,500 when I do this.
But I don't understand the visual thing of this, though. Yeah, we did.
So you can,
I'm gonna get it for
when you have different value resistors in,
Okay.
Yeah.
then you have to use this formula with the values of the
Oh,
resistors are different.
gotcha. Yep.
So whenever, this is what you gotta remember. And the particular formula that I always use is this one. If you just pick the formula, no matter if dividing C and multiplying these, as long as you,
Because the holes are kind of a little pushy.
remember one of the formulas is get through the test.
Good easy touch.
But here, we gotta remember that E also means voltage.
Yeah.
That's the hard part.
Louis, you okay? Everything good?
This is.
Thank you.
That's voltage.
And also,
But, yeah, so there were lots
You know,
of,
you
there's lots
could
of.
build on this.
as far as resistance,
Yeah.
just did
Oh,
that.
it was.
Measure across the resistor, see if it's right. Now, if we wanted to measure the current, we run into a snag. In order to measure the current flowing through that circuit, we have to break the circuit and insert an amp meter to measure the current. So, let me get rid of what don't need to be there. Okay, so our circuit's like that. We want to know what's the current flow, total flow going down, around, coming all the way back around again. Okay, if I take my own meter, I got power applied, and I put my own meter on here, what's it going to do with power applied?
Short out.
It's going to go ballistic.
Like
Because the old
meter.
meter says, I see voltage, I don't know what to do with that. Now, with digital meters, it won't hurt a thing. It won't hurt the meter. If you do that with an analog meter, you can blow up the meter. Because the analog meter is not geared to handle that. It won't put up with it. So we've got to do something different. So what do we do? Well, we have to break the circuit. Get rid of some of this stuff. We got some room here. Break the circuit. And place our meter on the amperage scales in series with everything else, so that the current flowing all the way through the resistor, flowing through the meter and back to the battery. Now, in most cases in real life, that's not practical. You know, you're working with a radio or you're working with some circuit, you don't have a real way to go in and open up the circuit, break a trace and all that, you know, you just can't do that. That's why we use Ohm's law. Figure a resistor that's carrying the current and calculate what it is. That's the whole point behind doing that. Let's take another little what if. You've got your mobile radio. Lance, can I go to the other side of the board? It'll be okay.
Shout about that.
So you've got your radio here. That's supposed to be an R. And we're going to hook our 12-volt car battery to it over here. So when we hook that thing up, we would normally go off the minus and go to that one, and we'd come off the plus and go to the plus. Hooked up like that, what am I missing? Fuse. You never do that. Never do that. Instead, a little funny thing like that represents a fuse. Most people recommend you put a fuse in both lines.
That's amazing.
There's a reason for that too, but we won't get into the reason for that right now. But anyway, with that, then I turn the radio on as well. How do I figure out how much current that radio is drawing on receive and then on transmit? Can I find out? Well, there's two ways. There's always two ways to do everything, right? Number one, I can come in here and break one of these traces and insert my amp meter. How much current do most transceivers draw on transmit full power?
HF or UHF?
Yes, either one, VHF or UHF or HF.
HF on 100 watts is going to be higher.
HF on 100 watts, generally going to be looking at around 20, 22 amps. Amperage, not milliamperes, but amperage. And your VHF, UHF radio, oftentimes on full power, 45, 50 watts, will still be drawing somewhere around 10 or 12 amps. That's a lot of amperage. Most of these meters we have will only measure 10 amps. So even if I broke my circuit, you notice there's special jacks on the meters for amperage. So I use that special 10 amp circuit and I hook it up in there and I turn the radio on and I transmit and it just says over, out of range, over limit. Can't read that high. Now what do I do? Well, there's another way to do that. Instead of doing that, if we could get in here where we could put our voltmeter across the fuse and measure the voltage drop on that fuse, we can calculate the current. Can we do that?
If we know that, it's these uncertain.
Now, that brings up the next question, though, where do I get the resistance value? I need to know the resistance value of the fuse, so I'm gonna have to measure the resistance value of the fuse. Usually those fuses are very large. Well, obviously they're like 25 amp, 30 amp fuses. But you'll have to have a good meter that will let you measure that small value. Maybe it comes out to 0.8 of an ohm or 1 ohm or something like that. But it's small value. But then you know the resistance, you know the voltage. Now you can calculate the current using Ohm's law. So you check it on receive, make the calculation. Check it on transmit, make your calculation, and you know you're good. Why would you want to do that? Is there a practical reason you might want to do that?
How big a wire around?
How big a wire? Which is a good point. The bigger the wire, the less resistance the wire itself has. So if you're running this wire from your battery to your radio and it's all the way in the back, you need a bigger wire for that than you would if you had the radio right next to the battery. If you got a big truck, for example, you know, the battery's way up in the front, and the radio's way back up in the back seat in a long truck. Needs some good wire for that. That's one way. What about your people? People are telling you, wow, you just really sound weak. I can just barely hear you. And you're thinking, well, it's supposed to be a 100-watt HF radio. What's the problem here? Well, that might be one of the places where you can check. See how much current drain. And you check it, and lo and behold, instead of drawing 22 amps on transmit, it's only drawing 3 amps on transmit. We say something in the radio is going, you got a problem with that. Now, let me go ahead and quickly say this, because if I don't say it, somebody will try it and say it doesn't work. With HF, when do we consume power on transmit with an HF radio? This is ham radio 101 now.
When you're modulating,
When we're on single sideband, we're only transmitting power when we're injecting the signal, not that as we're talking, right? If you just key a single sideband radio, HF radio, just key it, no talking, no sound, you're not pulling any current to speak of, maybe an amp, so just a tiny little bit. But then when you whistle into the mic, all of a sudden the power jumps way up because now you're using power flow. So when you want to do this kind of a power measurement, you got to watch out and do one of two things. Either make sure you get a good signal, a good strong signal in the mic, like whistling into it is probably the best. Or switch the radio to either AM or FM if you have those modes, which most do. And then RCW, either one, and key it. That'll be a constant. The current draining will be changing with the modulation that you're putting noise into the microphone. So that's just something to watch out for.
So if you're on FM and you key it, it's gonna draw, I mean, depending on how many watts it's gonna draw what, 23 if you're on, if you're on HF, but if you're on HF, you're gonna be on single sideband, so.
But normally, in most cases, we'd be on single sideband, but most radios will also let you transmit AM or FM on HF or CW.
And CW behave
Or
like
CW. CW will work also, it just doesn't have any modulation. The point being that it gives a solid drain on the battery when you keep it light, whereas single sideband does not. Single sideband is not very good. That's just a gotcha to watch out. So my point being, there are times when this can come in handy, you can actually use this kind of stuff for something you might want. Any thoughts about any of that? Of course, if you're really good, you like to break into circuits and do that stuff, hey, go for it. It's okay. Anybody have an RV? Anybody in here have an RV? Most of the RVs have a voltage monitor of some sort to monitor the battery voltage that the trailer or the unit has. And they will use a shunt to measure that. They'll have a very low resistance piece of metal somewhere in that battery circuit. Just like we measure across the fuse, they'll measure across that piece of metal. That piece of metal, very low resistance, but it will drop a tiny bit of voltage. They measure that to know the amount of current pulling from the batteries. So it is a very practical thing for that. Opens and shorts. This is where we get into trouble. The terminology messes people up. That's really what it is. Some people will call it a short or an open. Some people will call it an open or short. Some people will call it a short anytime something doesn't work right. What do we mean by that? An open just means that the circuit has been broken. There's a lack of continuity somewhere. The current cannot flow. A short, on the other hand, means something's been bypassed. If I short these resistors, it's much stuff up there, I can't see them. Okay, Bob, you're losing it. I guess I need to rag over. I guess so much stuff there, we can't see what we're doing.
This might be an easier concept with a light bulb.
Or fuse.
Yeah, let's start over. That's a good idea. Let's go back to the light bulb.
And you can actually try this on your breadboard.
Okay, back here on the light bulb circuit. Everything's hooked up, close the switch, the light comes on. Somewhere along the way, I run into a snag, and these two wires on a little socket wind up touching each other. That's called a short. That is a little short circuit. We have short-circuited the path of the current flowing through there now, so now it goes through here. Current will always take the path of least resistance. So it's going to go through that little short circuit right back to the battery. It's going to drain the battery like a bandit, and the light's not going to come on. So that is a short versus an open. If I break the circuit, then that's now an open circuit. That's the difference between the two. And I was going to bring some fuses, and I went off and didn't have enough to go around, so I can't do that. But fuses are an interesting thing to check. Fuses we don't check for a short. Technically, I mean, a fuse is supposed to have continuity through it. It is shorted. But a lot of fuses you can look at and you can see it's burned out. You see a little burn place right in the middle of the fuse element inside the glass or plastic holder. But some you can't. Some are opaque, some are just, you just can't see it. I've actually seen fuses also disconnect over by where the cap of the fuse was located, where you couldn't see the disconnect, back up under the cap, under the metal cap on it. So, we need to check, always check the fuse with an ohm meter. Should read near 0 ohms, like a tenth or two of an ohm, maybe almost nothing. If you measure it and you measure no resistance, not totally open, your total high resistance, in other words, it's open. So the fuse is no good. That's all it amounts to. Thoughts about that? Okay, that's pretty straightforward. Okay. We change the plot, see if we can do something a little bit different here. I'll tell you what, I cannot keep up with this.
There's a lot of stuff.
Okay, we're going to make a new circuit here. Okay. We've got 5 series connected nickel cadmium cells. What is the voltage on the nickel cadmium cell?
1.2.
1.2. Good. NiCads and nickel metal hydrides are 1.2. What is the nominal voltage in most cases on a lithium ion battery?
3.6 volts for one cell.
Exactly. They will nominally put out about 3.6, 3.7. When you first charge it, oftentimes you'll see up to about 4.2 or something like that. But 3.7 and 3.6 is the nominal voltage for lithium ion. But we're going to use NiCads here. So NiCads are 1.2 volts each. Times 5 of them would give us what voltage? 6 volts, right? Okay, so we got 6 volts. We know that. What's the resistance of the bulb? When it's light. We didn't measure this while ago. We talked about it, but we didn't measure.
I measure 4.5.
Better 4.5 when it was on.
So I measured 4.5 when it was off,
Okay.
but then when it was was on, I think it went to $45. I think.
We'll just pick it back. We'll say that when the light is on, it's $45. Because as Tim said, the value changes on the filament bulb from when it's cold or when it's hot. When it gets hot, the resistance goes way up. And of course, to measure the amount of current flowing through that and calculate the value of it, we'd have to break the circuit, put the ohmmeter in it, or we'd have to calculate it by measure voltage drops or something. We're just going to go ahead and decide it. That same light bulb is probably going on cold, 45 ohms while it's on. Okay, so we got 6 volts, 45 ohms. What is the current flow?
4.5, by the way. The resistance of the bulb is 4.5 ohms.
That's when it's off.
I know,
Is equal to-
it won't change that much, but that's a good enough measure.
Right. So we got 6 divided by 45, which is what, how much?
0.1333 endless threes.
Say that again.
I have 0.1 with endless number of threes.
Okay, let's just say 113. Okay, so the 13, or 113 amps or 130 milliamps, if we want to convert it to milliamps, that's the question. Okay, so with that, how long would that light stay on if those batteries are rated at 1,000 milliamp hours? What does that mean? Okay, batteries are rated in ampere hours or milliampere hours, and it's a small battery, which theoretically means that one of these batteries rated at 1,000 milliamp hours could deliver 1 amp of current for 1 hour. Now, they're hooked up in series to give us the 6 volts, so that's still going to remain the same. Value's still going to remain the same. Now, but pulling 45 ohms, what was that, and 113 amps, how long will that light actually stay on?
7 hours.
Anybody got a guess? How do we find out? 1,000 milliamp hours divided by 1.3 is how much?
130.
I did 130.
127
1,000 divided by 130.
is how much?
7.69.
7.6, okay, so about 7 hours.
A little over
A little over 7 hours. We're just basically dividing that, dividing the time, dividing 1.13 into the 1,000 milliamp hours. So we get a pretty good idea about how long those batteries can last. Now, how do we translate that into something more practical? We're going to find out in the field.
Yeah, we are.
So we want to run on battery or field, right? So we're running those wonderful HF radios that only like a full 22 amps full power. First of all, are we going to try to run all the HF radios full power until they work on battery? Maybe, maybe not. Maybe, maybe not. But so we've got, say we've got a 25 ampere hour battery, which I've got a lithium ion phosphate battery. It's good rated at 25 amp hours. So if I put that out there pulling a 12-volt radio, which technically the voltage fully charged is about 14 something, about 14 volts. But anyway, I can kind of get a good idea if I was transmitting constantly, pulling a certain amount of amperage from that battery, about how long that radio is going to last with key down. Now, we're not going to sit there with the key down on the radio the whole time to work. We're going to listen, get the information, key down, give our information, turn loose again. So it's going to be sporadic. But all of that, we can say, I'm just going to pull a number out there. So with my 25 amp hour battery, and I'm running 50 watts on the radio, then I say, okay, I did power that radio, key down, full transmitting for 4 hours. I don't know if that's even close or not. Let's say 4 hours. So I can expect 4 hours use. But the fact I'm only running probably a 50% duty cycle, that is, I listen for 5 seconds and I key down for 5 seconds. I listen for 5 seconds, key down for 5 seconds. Then I probably get close to 8 hours out of the battery. You do it going that route. Conversely though, if I crank the power up, what's going to happen to the battery life and the time? Time's going to go down. It's going to sink like a rock. So those are some things we may be looking at in the field, depending on how much power we have at our disposal. If a couple of people come out with their big lithium-ion RV batteries, they're 200 amp hours each, we probably have more power we know what to do with. But we can still calculate it if we need.
And if we're feeding the battery, recharging the solar panel.
And I'm sorry,
If you're recharging the battery
Oh,
with the
yeah.
solar panel at the same time.
and if we're recharging at the same time, which is good, and when you hook the solar panel to it, when you're not keying, you're generating more with the solar panel than you're using on receive, so yes, it'll be charging. And then when you're transmitting, you're using the solar power to add to the voltage of the battery. So it extends the battery a lot. You heard about the big contest that some of the college students had, I hope. The 3 college students were competing for a big science scholarship. And the guy from MIT came into the committee, he presented his plan. He said, I have designed a completely computer-controlled operation that will take a rocket ship, take off automatically on Earth, control everything, circle the moon, take pictures, and come back and do a soft landing on Earth. And he had reams of paperwork. And I've never seen anything like that. That's brilliant. But we have to interview the other 2 candidates. So we brought the next guy in, who's from UCLA, and he said, basically the same thing, but I've designed a thing to go to Mars and back. He had twice as much paperwork. They were just amazed with it. Then they brought the Aggie in. Aggie said, I got a long beat. I'm going to send a rocket ship to the sun. I said, you can't send a rocket ship to the sun. It'll burn up. I said, sure, I got it figured out. I'm going to send it up at night.
That was a long way to go for that.
So, all that being said and say,
I was wondering if we were gonna get a joke today.
all that being said to say that, when nightfall comes, our solar panels don't do us too much good. There used to be a standard April Fool's joke in Popular Electronics magazine. They would do a solar night light. A solar cell with light. Obviously at night that doesn't work. That's the discussion. Okay. Actually, we're a little ahead of schedule. We're doing good. It's just 11 o'clock. Any questions or thoughts? Anything you want to play with, you're welcome to play with. Otherwise, I think we're pretty much through. Any suggestions or thoughts? I'd love to hear about them. You can email me if you like, or an easy way to get a hold of me is my call sign, K5CRHam@gmail.
Well, you got some ideas for some other classes, but I think we should do that if you're willing.
Oh, I love to do it. Now, the AC class, we won't get out early this year on that one. We'll be pushing the time limit for that one because there's so much to do.
I just want to say, I mean, I've only been licensed for about 2.5 months. Maybe, I mean, it was like the beginning of April when I hadn't gotten my job. I mean, this type of stuff is outstanding to be able to take what you read in the manual and actually put it into practical application. And I just want to say I appreciate you guys holding this type of thing because it's